Apologies, guys. My connection is really not great today. Please bear with me. We're going to try our best to make sure that we can keep the session going as best as possible. As I was mentioning, we are on the road this week. A lot of you guys would have seen us at your schools helping you with applications. So when we are traveling, we do come across some connectivity issues. And finally, I now know what you guys go through every day when you have these connectivity challenges. So I'm going to be a lot easier on you. Okay. So I'm going to just ask you guys just to be with me today and then try and communicate a lot. So I'm going to keep telling you guys, please check my screen share, all of those things and see if it is okay and working. So please, if you guys can see my screen, I'm showing a page that says work, energy, and power, and it's got summaries on it. If you can see it, please just put a thumbs up in the reactions, and I know that you guys are with me for the session so far. I get some thumbs up. Fantastic, guys. Thank you so much. Really appreciate it. And then let's try our best to really help each other through this session. So let's quickly go through our summary and let's see how this session is going to go for today. Right. So with work, energy, and power, we're starting off with the concept of work, then we'll go into energy, right? So what I like to do often is I like to start the other way around. I like doing it with energy, then work, then power, right? So now what I want you guys to first do, right, is tell me what is energy? What is the definition of energy? Please post in the chat what you guys think the definition of energy is. That would be very useful to hear from you guys. So post in the chat. If you want to say it out loud, put a hand up. We'll let you unmute. But for now, post in the chat, what is energy? Give us the definition of energy. I'll give you guys 10 seconds to think about it. Thank you so much, Refilwe. Energy is, and thanks, Tato, thanks, Precious, the ability to do work, right? You guys are doing very well with our definitions today. So energy is the ability to do work. Think about it. When you've had a long day, hawaja, you've had nothing to eat, and your energy levels are very low, and someone asks you to help them carry a desk from the hall to the one classroom, you are almost unable, right? Because without energy, you can't do any work. Very, very important, right? Now, then the question comes, now that we know what energy is, the ability to do work, well, then what is work, right? And then that's the definition we see on our screen now, that work is done when a force is acting over a displacement, right? So when a force is applied to an object and that object moves a distance in the direction of that force, work is then done. And a nice, easy way to look at it is that work is what happens when energy is transferred from one object into another. So if you take a ball in your hand, that ball is sitting there and you kick that ball. You are now doing work. You apply a force to the ball is going to move a direction, a certain distance in that same direction. And that ball now has kinetic energy. You've transferred some of your stored energy that you ate earlier on in the day into kinetic energy that the ball now possesses. So whenever you then give something else energy, you are doing work. So energy, number one, let's quickly recap. Energy is the ability to do work. Without energy, you cannot do any work in the first place. And then once you've got energy and you can do work, what is work simply? Work is you transferring any amount of energy that you've got. And then finally, the power definition. Power is the rate at which work is done, right? So if you've got energy, you can do work. Now that you're doing work, what is power? Power is the rate at which work is done. How quickly can you do that work? Are we together? Imagine a drag race. If any of you guys are on YouTube, you probably have, the channel called Wow, where all they do is drag races every day, all day they do drag races. So think about this, right? Because work is force times a distance, the energy it takes a car to go from point A to point B is the same energy. So if I need to take my Ford Figo from point A to point B, and you take your Golf 7 from point A to point B, we are going to expend the same amount of energy, right? The same work is going to be done to move the car from point A to point B. But why is the Golf 7 more quicker in that process? Is because it's more powerful, because it can do that energy and it can do that work a lot quicker. That's the only difference. So when you say a car is more powerful than another car, what you are saying is that it can do the same work as another car. The difference is it does it quicker. And that's how certain cars are more powerful than other cars, even though the energy required is no different. The energy required is exactly the same amount of energy. Okay, let's quickly finish looking at our summary there. So again, we need to look at the idea of what is positive work, what is negative work. Remember, I told you guys that work is simply transferring energy from one to the other. So positive work then says to us that we are transferring energy, right, to an object by the force. So when you do positive energy, it means you are going to increase the energy of whichever object you are doing work to. Negative energy means you are removing energy from an object. So if a car is moving and I'm trying to stop that car from moving, right, I am doing negative work. Negative work meaning I'm removing energy. I'm slowing the car down. I'm taking away its kinetic energy. So make sure you understand those two concepts. They come very, very important in the later section. Then we've got the equation. W is equal to F delta X cos theta, right? Where W is going to be our work. F is the force that is doing the work. Our delta X is the displacement of the object, and theta is the angle between the force and the displacement. Please don't confuse that with the angle of the incline. Very, very important. Theta is not always the angle of the incline. Theta is the angle between the force that's causing the motion and the direction of the motion itself. We'll have a look quickly at why I say that particular statement. So when we look at the examples there, we've got an object there, a block. We're talking about this block now in particular, where in that block, we've got a force of 10 newtons moving an object the distance or displacement rather of 5 meters. When we calculate that, we then say F is 10, delta X is 5, and the cos theta is 0 because the angle between my force and my displacement is going to be 0. The one on the right-hand side, this block over here, we now have a force acting at an angle of 30 degrees, right? Moving the same distance, 5 meters. Now, when I do the calculation, my force is 10, my distance or displacement rather is still 5, but I now add cos 30 because there's an angle between the force as well as the displacement. So that angle of 30 degrees that we can see here is what we're going to put into our calculator. Now we can see that my angle that's acting at an incline is doing less work because not all of your energy is focused in one direction, the direction of motion, right? Then we can see scenario number 4. We're going to have the object is supposed to move this way. The force is now perpendicular, right? Perpendicular meaning at right angles to my motion. Let's plug that into our formula, right? So force is 10, our distance is 5, and then cos 90. And then if you guys remember from trig, we did trig just yesterday. What is cos 90? Cos 90 is actually 0. So anything times 0 will give you 0, meaning a perpendicular force will do no work on a moving object. Very, very important, right? You can see here, NB, a force acting perpendicular to the displacement does 0 joules of work. Very important. And then finally, here's an example of negative work being done. So an object is moving to the right, but the force is acting to the left. So when we do that, we say F delta X cos theta, the force is 10, the delta X is 5, and the cos theta is 180. Why do we say 180? Because if my motion is this way, I need to measure the angle like that. And that angle between motion and force is going to be 180 degrees. Very, very important. And then cos 180 is -1. That's why you see this is going to be -50 versus the 50. So the first one is going to be positive work. This one is going to be negative work. Very important thing to pick up. If you guys are still with me, give me some thumbs up in your reactions. If this doesn't make sense, please post a very specific question in the chat. I see some thumbs up. Thank you guys very much. I appreciate that. All right, let's move on. So now let's look at work done by gravity, right? So work done by gravity is basically any work done by the gravitational force of the earth on an object. So if an object goes up, the work done by gravity is negative. Remember, what does negative work do? Negative work takes energy away from you, or negative work makes it harder to do what you're doing. So when you jump off the ground and you want to go up, gravity is pulling you down, right? Gravity makes it harder for you to go up. That's why it's negative work. It takes away your kinetic energy. As you jump, you slow down in the air because you have that force acting opposite to your motion, negative energy. Now, if an object goes down, so imagine you're standing somewhere high and you drop something to the ground without having to throw it. it'll get faster and faster and faster. Because why? You've got the motion and the force acting in the same direction. Now it's giving my object energy. So as I drop it, my gravitational force is going to give me more and more energy. I'm going to get more and more speed. That's why it's positive work. So if something gets sped up and it gets faster, it's probably going to be due to positive energy. If something's going to get slower, it's going to be down to negative energy. So we can see there the work done by gravity is simply going to be, think back to F delta X cos theta. So my force of gravity is going to be mg, right? The negative just says that I'm acting in the downwards direction. And then you're going to say delta H. So the reason why we say mg delta H is that now your change in potential energy is going to be a similar thing to the work done by gravity, right? That's very important. I'll show you guys later how those two equations come together. And then when you're looking at an object on a slope, there's two ways to calculate the work done by gravity. I can either use the slant distance, meaning the distance on my incline, right, times FG parallel. That's option one. Option two is I'm going to use my vertical distance, right, times FG itself. Very, very important. So if I use my slant distance, I'm going to use FG parallel. But if I use my vertical distance, I'm going to use to note those two facts. And then we're almost done. How do we calculate net work? Net work is calculated similarly to how we calculate F net, right? It's the sum of all the forces. That's F net. Net work is the sum of all the work being done on a particular object. So if we then say W net must break down into, well, what are the various factors causing this object to move? So we could have W applied, meaning there was an applied force. There could be friction. There'll be work done by friction. There could be gravity. Even if not on Earth, there's always gravity. So there could be gravity, and then you'll get work done by gravity. You take all of those factors together, and that'll give you your net work done. Now, again, calculate F net and find the work done by the F net. Then you can simply say W net is equal to F net times the distance times cos theta. That'll also work. Another way to look at work net is using your work energy theorem, where W net is equal to change in EK. Change in EK is going to simply just be your half mv squared final minus half mv squared initial. Or sometimes people like writing it as half m, then you say vf minus vi squared, just like that. Okay, that also works if you need to do that. So remember, you have to find VI or VF. Then second last, we're looking at conservative and non-conservative forces, right? So the work done by a conservative force, that work is really independent of the path taken. So basically what I mean by that is that it doesn't matter what path the object took to get from A to B. So remember, the work done by a conservative force is independent of the path taken. So let me give you an example. The work done by gravity is the same whether the object went, if this is point A, let me quickly mark down, if this is point A, and the object went the same as if we were saying an object went from point C down here to point D. Because how do we calculate work done by gravity? Remember, let's go back. Work done by gravity simply is going to be either I'm going to take this distance times FG parallel. Very, very important. Those are the two options I've got. So in this case here, I'm going to either do that and use FG, or I'll do that and do FG parallel. But either way, I'm going to get the same answer, because when you calculate it, you'll see, we'll do examples later on, and you'll see that the numbers don't actually change, right? It's different to something like friction, right? So work done by non-conservative forces depends on the path taken, right? So example, the work done by friction will differ in the below scenarios, because friction has been experiencing what you've been experiencing, right? The longer you've been going through this journey, the more friction you're going to experience. And another way to think about it, right? When I say conservative versus non-conservative, you must think about when you're doing conservation of means I don't gain or I don't lose overall. So let me give you an example. Let me quickly erase this. So if we're looking at a scenario where this 2 kilogram object is going to move from A down to B, right? Sorry, someone just posted something in the chat. My friend said, we'll take that up with our team. We'll double check. Also remember, guys, you don't just attend for 5 minutes or don't register and think that counts as attendance. You must attend the whole session. It's very, very important. Okay, let me come back to my session here. If that 2 kg object moves from A to B, right? I want you guys to post in the chat. Is gravity doing positive to B? Is that positive or negative work? Quickly tell me. Post in the chat. When the 2 kg object moves from A to B, does gravity do positive or negative work? Think about how we described positive work and negative work. Positive work is going to increase your energy. It's gonna add to your speed or something. It's gonna increase energy, right? There we go. Positive work. Fantastic, guys. Thank you for that answer. So when we go down, you're gonna get positive work. Now let's consider a scenario where I'm moving back from B all the way to A. Does gravity there do positive or negative work? So the object is now on the ground. I need to move it up. Does gravity do positive or negative work in the green scenario? There we go. So the green scenario, my work done by gravity is going to be negative. So let's think about the term conservation, right? And a conservative force. So a conservative force, another way to think about a conservative force, the net work done by a conservative force around a closed loop. What I mean by a closed loop, if I start at one place, go somewhere and come back. So that's a closed loop. I end up where I started. So the work done by a conservative force on a closed loop will always be zero. So you can see from A to B, gravity adds energy. It does positive work. But from B to A, it takes that energy back. And when you look at it, it'll be the same amount of energy. So from A to B and back to A, net work done equals zero, right? But let's look at friction, right? So if I took now an object, there's that object that we're looking at there. It starts at point A and goes to point B, right? Okay, sorry. Masero just asked the question. Masero says, sir, are conservative forces non-contact forces? So you can find conservative forces that are contact forces. You can find conservative forces that are non-contact forces. I'm going to give you a little cheat code for today. The cheat code is, as grade 12s in South Africa doing the CAPS curriculum, the only conservative force you deal with is gravity. There's my cheat code for you guys. You don't have to worry about very many things. But let me give you examples of where contact forces and non-contact forces come in. So remember, gravity is a non-contact force, right? You don't have to be in contact with something for it to have a gravitational pull on you. If you jump, you're not in contact with the earth, but that earth will pull you straight back down and you'll probably break something. Non-contact force. Another example of something that's going to be a conservative force is a spring, right? So you remember how gravity, if I go up, it works against me. If I go down, it works for me. But think about a spring. A spring does a similar thing. If you try and compress a spring, right? Any kind of spring that you try to compress, it's going to work against you. It's going to be very hard to compress a spring. But when you want to go back in the direction of a spring, it's going to work with you. It's going to push you away. So a spring is another example of a conservative force. A spring force is a conservative force, but you don't deal with spring forces in grade 12. So for now, don't worry about it. The only conservative force you will deal with in CAPS is going to be a gravitational force. Awesome, guys. Then let's look at the second scenario. So we're looking at that object there, 2 kilograms, is going to go from point A to point B. Then there's a force of friction. So I want to know the work done by friction. Is that going to be positive or negative work when that object goes from A to B, right? Think about it. What is positive and negative work? Positive work aids in your giving you energy. Negative work takes energy away from you. Thank you so much for myself. Already gave us one of the answers there, right? Friction does negative work. So when I go from A to B, friction makes it harder for me to move. It'll be negative work. Now, what about the scenario where I'm moving from B to A? Will friction do positive or negative work moving from B to A? Post there in the chat. Let me see what you guys think. Rifanola says negative. Does anyone else have a thought? Rifilo says negative. Bitumela says negative. Thank you guys for your answers, right? So again, when we deal with this scenario, even going back, the work done by friction is going to be negative. So notice how when I go from A to B, it's negative work. From B to A, it's negative work. If I do my net work calculation from A to B and back to A, I'm not going to get zero. I'm going to get even bigger negative work than I started off with. Therefore, friction is not a conservative force. Because a conservative force, if I go in one direction and I come back to where I started, my net work must be zero. That's how I know I'm dealing with a conservative force. And in this case with friction, my network is not going to be zero. It's going to be a very big negative amount of work. It will remove energy in my system, both directions. So that's another nice way of looking at conservative forces. But the key definition to remember is that a conservative force is a force that where the work done by that force is independent of the path taken. Very, very important. Okay, let's quickly wrap up the last two parts, and then we can jump into some fun questions, right? Then let's look at, again, WNC when you're working with non-conservative forces, right? So usually friction and applied forces are going to be non-conservative forces, right? So use this formula when there's a change in height of the object in a scenario that is known. That's the WNC, where WNC is equal to change in EK plus change in EP. And then finally, the one that normally people start with, but I like ending with it because it's the one that's sort of more easy. It eases you into things. It's mechanical energy, right? And remember, what is mechanical energy? Mechanical energy is the sum of our potential plus our kinetic energy. So if you see our potential energy there is mgh, but potential energy is the energy of height, right? Kinetic energy is half mv squared. Kinetic energy is the energy of velocity. Why do I say these things? Let's have a look. So when you're dealing with potential energy is mgh. So I've got mass, I've got gravitational acceleration, and I've got height, right? So an object's mass is not a variable, right? If I weigh 100 kilograms right now, 2 seconds later, I will still weigh 100 kilograms. It's almost impossible for me to change my mass as quickly as I can change my velocity. Gravitational acceleration is a constant, right? It'll be the same depending where you are at that place. But height is a variable. Height is a variable because it means I can at any given time, if I wanted to, change my height simply by jumping. So height is the variable, which means potential energy is the energy of height or elevation. Let's go look at kinetic energy. Again, we said mass is not a variable. Your mass is going to be a constant. Half is a number half. Even if Jesus comes back today, half will still be half, right? What is the variable in that case? The variable is going to be the velocity, because I can be standing stationary one moment and then I can be sprinting the next moment. Okay, so then we need to think about when you see an object in motion, velocity equals kinetic energy. If an object is elevated above the ground, that is your potential energy. Mechanical energy will simply be the sum of the two. At any given point, your EP plus your EK will equal your mechanical energy, which will bring us then to what we call the conservation of mechanical energy. And then what does that state? In an isolated system, the mechanical energy will remain constant. And there's our definition over there. Let me just make it a little bit bigger. In an isolated system or a closed system, the mechanical energy will remain constant. Some of these things then come out that at a maximum height, your EP is max and your EK is minimum, right? Usually at maximum height, your velocity will be zero. We saw that when we were doing, what's this topic? Vertical projectile motion the other day, right? At maximum speed, EP is going to be a minimum, right? At maximum speed, usually it means if an object is moving on a slope or whatever, your height will probably be at its lowest if that's the maximum speed for your motion. Okay, that's very important. Again, when do we use this equation of conservation of mechanical energy? We use it in an isolated system where there's vertical displacement and also when there's only gravity acting on an object. So let me quickly give you my cheat sheet of how to go about this topic. So my cheat sheet of how to go about this topic is going to be as follows. You're going to look at your question, right? And then you need to think about a few things there. So in my question that I'm dealing with, what is the scenario? What forces are there in play. So the first question I ask myself, what forces are acting? If you have a scenario where it is only gravity that is acting on your object, you know you're going to use conservation of mechanical energy, right? Because you're dealing with conservative forces. So you're going to say E mech before equals E mech after. That's what you need to do. Especially, these are those questions that say using energy principles. Let me write that here. Those questions saying using energy principles. Excuse my spelling. This is how you answer those questions. So think about what forces are going to be acting. If it's only going to be gravity, you're dealing with a conservative system, conservation of mechanical energy. If it's not just FG, now you must consider what is really happening in that case there. If it's not just FG, you're going to use one of the following equations, right? You're going to either use, so in this case is not just FG, you're going to either use work energy theorem, W net is equal to change in EK, or you're going to use WNC is equal to change in EK plus change in EP. And let me try and bring all these things together for you, right? So remember, this equation in red is an equation for dealing with conservative systems when I only have conservative forces. What is the opposite of that? The opposite of that is a non-conservative system. So when the equation says in an isolated system, the mechanical energy remains the same, meaning my E final minus my E initial is literally just going to be zero. Because if I take this equation and I take it further, imagine if I take this equation further, and what I do is I move E mech before to the other side. What do I get? I get 0 is equal to E mech final minus E mech initial. What is that? E mech final minus E mech initial is equal to my change in E mech. It's change in mechanical energy. So my change in mechanical energy will be 0 because it's a conservative system. Versus, if I look at this question here, WNC, the work done by non-conservative forces, right, is equal to change in EK plus change in EP. What's change in EK plus change in EP? If I have change in EK plus change in EP, it means I've got a change in EK plus EP, right? What is EK plus EP? It's E mech. It means I've got a change in E mech. And what caused that? My WNC caused the change in E mech. Because again, only non-conservative forces can change my mechanical energy. If you're dealing with a conservative force, which is gravity, you will have no change in your mechanical energy because you're dealing with a closed system and only conservative forces. I hope that makes sense, right? So if you've got a system with only gravity, no friction, no applied force, conservation of mechanical energy. If I've got now friction and I've got an applied force, I'm going to use one of the other two. How do I know what I'm going to use? Remember, kinetic energy is the energy of motion, potential energy is the energy of elevation. If I've got a change in velocity only, I'm going to use WNC. I mean W net. If I've got a change in height and a change in velocity, I'm going to use WNC. So in this case here, W net is equal to change in EK. I only use when I've got change in velocity only and no change in height. If I've got a change in velocity and height because of non-conservative forces, I will use WNC. All right, let's do a question and see how we can apply this knowledge that we have been looking at together. I'll give you guys 2 minutes to ask any questions before I jump straight into our questions. Okay, I don't see any hands up and I don't see any questions in the chat. I'm going to jump straight along. Here, you can still see my screen share. Okay, sure. Cool. So let's do question 5, right? Question 5, as we can see it there, is going to be a question that is dealing with work, energy, and power, right? So in this question 5 that we're looking at, we are really going to try and figure out, using everything we just learned, how can we put all of these things together? How can we then answer this question, especially utilizing our energy principles and everything we've just learned? Cool. So let's start by reading our question. It says a 12-kilogram block is initially at rest at point A. So point A, we know is something important. There, it's initially at rest. The saying initially at rest gives me a certain amount of information. Please tell me in the chat, what does that mean? If an object is initially at rest, what information am I supposed to gain from that? Fantastic, right? My initial velocity is going to be 0. So I know there that my velocity is going to be 0 at point A. At the bottom of a rough inclined plane, there's another thing that we need to catch from that. What is this? And they even put it in all capital letters. What do we know when they say that our inclined plane is rough? What information do we need to get from that? I'll wait for you guys. I'll give you 10 seconds to put that in the chat. Thank you, Sane. Thank you, Uteng. It means we have to deal with friction, right? So there's going to be friction in our particular question. So our friction is not equal to 0. We will have friction in our system. Inclined plane. The block is pulled up an incline by a constant force F. There's another piece of important information. We're going to have a friction, not a friction, but an applied force F acting parallel to the inclined plane. The block reaches point B, right? Which is at a vertical height of 4.5 meters. That's important information above the horizontal, with a speed of 2.25. So we know that this, again, is going to be the speed at which I reach point B. I'm going to write that and say my velocity at B is that value over there. See the diagram below? Then they ask us to define the term non-conservative force. I've said this so many times. You guys should have it memorized at this point, right? You guys should have memorized what is a non-conservative force, right? Remember, a non-conservative force is a force where the work done between 2 points is not dependent on the path taken. Very, very important, right? So it's a force where the work it does is independent of the path taken. Very important. Let's look at 5.2, right? 5.2 says, draw a labeled free body diagram of the block when it is pulled up the inclined plane. So we need to think about, at this point here, what I like to do is I like to look at the diagram first, figure out what are my various forces. Once I've got that together, then I take all that information to do my final free body diagram. Okay, so what I want us to do is to identify the forces that act on this object, right? And identifying forces is a very important skill when doing questions like this, because sometimes people tend to put in forces that don't exist, simply because when an object is maybe sliding down an incline, people assume something must be happening there. So already we know we're going to have, there's a force applied, which we can see over there, right? Because it was stated that there's a constant force F, right? It's being pulled or pushed. This word here tells me there will be an applied force. The next thing, I need to know that I've got an FG, right? Force of gravity, why? Because my object has got a mass. Anything with mass will experience a force of gravity, very important. The next thing again, this thing is resting on a surface. It's on a rough inclined plane. So this surface tells me very much right now that I'm going to have a normal force. So that normal force is going to be perpendicular to my surface. This is my F normal coming that way. Let me quickly just fix my FG so that you can see very clearly that my FG goes vertically downwards towards the center of the Earth. And then finally, we were told that this is a rough inclined plane. And this word rough here tells me that I've got a frictional force that must act downwards in this case here. right? That's going to be my force of friction. Those are my forces that are covered. I can now take all of that and go put my diagram together. So again, how do I do my diagram? You start off with a reasonably sized dot. So my reasonably sized dot is going to be here. Then I can add my forces. The first thing, I'm going to have my force of gravity. Apologies for that. I'm going to have my force of gravity acting straight down like this. Fg, or you can write weight as well. They will accept that. Then I'm going to quickly just put in a faint line representing my inclined plane so that I can draw my forces in the right way. So if I make this as a very faint line like this, so at least I know where my inclined plane needs to be, I can draw my other forces. So then I know my force applied is going to be directly up my inclined plane. This is going to be my force applied, or my force F as it was given to me. Then I've got friction acting downwards, down that same incline. That's my force of friction. And then perpendicular to my inclined plane, I need to have my normal force. My normal force, F normal, in this particular way. Very important. This is what your free body diagram needs to look like. And then once you've got that correctly, you know that you are ready to answer this question, right? Very, very, very important. They do, however, accept if you were to give a diagram. It's a personal preference of mine, not saying it's incorrect. It is a personal preference of mine that I don't like to draw a diagram that looks like this, but you are more than welcome to draw it, right? Where you'll do a reasonably sized dot. You've got your FG, wait, let me quickly do that, not that. You've got your force applied in this direction there. You've got your normal force perpendicular this way. And then what some people like to do, let me just make this dot a little bit bigger, is they like to have FG perpendicular, and then they'll put FG parallel. It's not incorrect. You will get your marks for doing this. It's just that when I do this, I don't prefer it. I prefer drawing the diagram with the forces that are there, and that's my force of friction. You will get marked correct for both of them, right? Someone asked a question there that Prudence says, is smoother surface indicating that there's no friction? 100%. And Masero even answered you, well done, thank you for that. If they say there's a smooth surface, that means there will be no friction acting on my object. Well done for catching that, guys. Let's do 5.3. 5.3 says, calculate the total work done on the block by non-conservative forces. You see, they even give you this is a through pass, basically, guys. You've got no reason not to get this. So when they give you non-conservative forces, your brain should immediately, NC equation is the equation I have to use for this particular question, right? So let's jump into this question now. The work done by non-conservative forces is going to be as follows. So you're going to say, well, my WNC is equal to change in EP plus case there. I don't even have to unpack my WNC because they asked me for the work done by non-conservative forces. So my change in EP is going to be M H initial plus my change in EK is going to be half mass times VF squared minus VI squared. And then when I can take that, I can plug the values in there. Let's quickly go double check what our values were, right? So we know our mass was given as 12 kilograms. We can see that there. We know what gravity is. Our initial height, we started on the ground. That's 0. Our final height is going to be this here. This is going to be our final height. Our initial height is going to be 0 on the ground. Then another thing we can look at is our velocity. So they said the block was initially at rest. We know that our initial velocity is going to be 0. And we were given a final velocity, right? This one here is our final velocity, 2,25. We can go substitute those values in and then see what answer we get. So in my substitution steps, I know my mass was given as 12 kilograms. Gravitational acceleration is always 9,8. Height final, we ended up at a height of 4.5 minus my initial height was 0, right? Plus half, my mass is 12. My final velocity was given to me as 2,25. Don't forget to square it. That's a place where people make a lot of mistakes. Minus 0 squared, and we've got that. Please plug that into your calculator and tell me what answer you guys get. I'll give you 2 minutes to do that, the calculator work. Thank you guys for your answers. You guys are doing really well. So the answer that you should be getting there is 559,58 joules. Here's a quick question for you guys, right? Post this in the chat. Is work a scalar or a vector? Is there a direction I need to include here, right? Is there a direction I need to include? Is work a scalar or a vector? Must I include a direction? If so, what is the direction? I'll repeat my question. Is work a scalar or a vector? Do I need to include a direction? If so, what is that direction? Well done, guys, right? Work and energy are both scalars, so there's no direction required. That is the answer that I need to give as my final answer. So my work due to non-conservative forces is going to be 559 joules, 0.58, and that's literally where it stays. If you are unsure about anything, please just ask in the chat, put a hand up, and we'll quickly go through this question again. If you are happy and you are on board with me, give me a thumbs up in the chat or give me a thumbs up as a reaction. See some thumbs up already there. Thank you guys so much. Okay, let's jump to our next one. Cool. So the next question now says, the same constant force now moves the block at a constant velocity across a rough horizontal surface from point B to C, as shown below. Force F acts parallel to the horizontal surface. Let's quickly unpack. There's a lot of stuff we need to check there. So the same constant force, so that force is going to be the same force as above, right? Now moves the block along. Very, very important. What does constant velocity tell us? It tells us that we're going to have no acceleration across a rough horizontal surface. Again, that tells us we are going to have friction from point B to C as shown below. Force F acts parallel to the horizontal surface. Then they'll come and say the magnitude of the constant frictional force acting on the block while moving from point B to C is 42 newtons larger. 42 newtons larger than the magnitude of the constant frictional force acting on the block when it moves from point A to B. Okay, let's unpack that. So there will be force of friction. So let me say this, the friction from A to B, right? Plus 42 newtons is going to be the friction from B to C. Hope that makes sense to everyone, right? It says the magnitude of the frictional force acting on the block while moving from B to C is 42 newtons larger than the magnitude of the frictional force acting on the block when it moves from A to B. Then it says calculate the distance from point A to point B. Hope that makes sense. Now what we need to do is we need to draw an action plan for this question, because the information they've given us doesn't seem like it's information that's going to be useful for us answering this question. But trust me, the information that has been given there is going to be useful to us. It's going to make a lot of sense. So what we need to now do is first figure out, well, what is that frictional force, right? Once we know what that frictional force is, we can then try and work this option together, right? So in putting that process together, we now can then take that and then do this a number of ways. So let's try and figure out. So either option A, what I will do, is I can then go find the friction from B to C, right? If that's possible, use that to find the friction from A to B. Once I know what the friction from A to B is, I already know the force. I can then use work is equal to force times distance because I know what the force from A to B is. I can find the force times distance and find the distance that way. That's one option, right? And I can use it to find my delta X from A to B. That's one option. Let's see if we've got enough information to figure that out in that particular case. So given that there, we know we're moving at a constant velocity. Moving at a constant velocity means I'm going to have no acceleration. What does no acceleration mean? Let's draw the free body diagram for that 12 kg block. So the 12 kg block will look like this. I'm going to have a force acting this way. That is our 10 Newton force. And then I'll have a force acting this way, which is our force of friction, right? Because there's no acceleration, I'm moving at constant velocity. My force applied must equal my force of friction in magnitude that we're together. It must equal that in magnitude, which means actually, because I know what the force is, I can actually go and find what the friction is. And then once I've got the friction, I can use the fact that it's now 42 Newtons larger, take that and then go and solve an option we can take. And then let's maybe try that option and see how far that option will get us. Cool. So let's start with that whole process there. So we said again, using Newton's first law, we know that my F net, this is now dealing from point B to C, right? My F net must equal 0. That's Newton's first law because I'm now moving at constant velocity. Remember Newton's first law, an object will remain stationary or in a state of motion unless a net force acts upon it. In this case, it's constant velocity because there's no net force acting on it, meaning F net is equal to MA, no acceleration, 0. What is my net force? If I say right is positive and I say left is negative, let's take all my positive forces minus my negative forces. So 0 is equal to positive force is going to be my force applied. Negative force is going to be my force of friction. Let's substitute our values there. We know that the same constant frictional force F, and we were told at the very beginning that this force apologies. In my brain, I thought they gave us a value for F. I thought they gave us. So we can't use that because we don't have a value for F in that case there, right? But it's okay. We'll use that same equation, right? It just means that we now need a second equation to help us solve this. Because what does that mean? It means I've got two unknowns. I don't know what my force applied is, right? And I don't know what my force of friction is from B to C and from A to B. But that's okay. So I'm going to call this equation 1. Like I said, there's always multiple ways we can solve certain problems. Don't know what that is. I'm going to call that equation 1. Then I'm going to now need to develop a second equation. How can I develop a second equation? I'll use my second step I was going to do. The second step that I was going to do once I have found everything, I was going to then say WNC, right, is equal to, well, what are our non-conservative forces? If we go back to this object, right, this is now dealing from A to point B. Our non-conservative forces, so if you look at your free body diagram, let's quickly go back. Where's that free body diagram from A to B? Quickly looking at this, force applied is non-conservative. We said force of gravity is a conservative force, so that doesn't count. NC is going to be our force applied. That's a non-conservative force. Force of friction, non-conservative force. Force normal doesn't do any work. So force normal doesn't do work. We're not going to include that. So we'll only include these two forces, force of friction and force applied. Then in that case there, WNC is going to be equal to my work done by friction and my work done by the force applied. It's going to be the work done by my force applied plus work done by friction. All right. In that case there, That's going to be my equation 2, right? Let's take that and then we're going to solve these two equations simultaneously. All right. Someone asked there in the chat, Edio, see Edio, I do remember you. I saw you today. So, sir, any force that is in horizontal, it has the same magnitude. So I'm assuming you're asking me based on this statement that I made here, right? That if the two forces are horizontal, do they have the same magnitude? No. So the reason why my force of friction and my force applied have the same magnitude is because they told me this very important statement here, that my block is moving at a constant velocity. What does constant velocity mean? It means I've got no acceleration at that point, right? If I've got no acceleration, my F net is equal to MA, but MA will be 0 because acceleration is 0. So if I then say, well, okay, what is my F net? FA minus FF. If I move this FF to the other side, I end up with this equation here. It means my forces must be balanced for me to have a 0 net force. Eddie, I hope that makes sense. So it means I'm going to have balanced forces from here to there. You can clearly see that, right? That's my equation 1. My equation 2, I'm going to use the second step I was going to do anyway. WNC is equal to work done by friction and work done by my force applied. So as I do that, I'm going to now solve them simultaneously. Let me unpack equation 2 first. And then I think at the very end, I can plug in my equation 1 to just finish off what I'm about to solve, right? So in this case here, I'm going to do the following. So WNC, we had a value for that. We calculated it, right? It was 559,58. My work done by my force applied is going to be what? It's going to be force applied times my delta X times cos of theta plus my work done by friction, right, is going to be what? It's going to be my force of friction times delta X times cos theta. Now I can go and substitute those values. Apologies, guys. We just had a power cut. I don't know if everyone can still hear me. If you can still hear me, please put a thumbs up in the chat. Then I know you guys can still hear me. Or put a thumbs up in your reactions. Okay, thank you. I think I'm still okay with power. Let's keep going. So let's keep going with this equation and let's try and take it as far as I can go, right? Left-hand side will remain exactly as it is, 559,58. The right-hand side, I'm going to try and work whatever I can work in that case. So in that case there, I know my delta X will be the same. My cos this won't be. So my force applied, let's quickly go back, right? From A to B, force applied is acting in the same direction as my motion. Remember that my motion was going up the incline. So force applied is acting same direction. So this is going to be cos 0, right? 0 degree, 1. Force of friction is going to be cos of 180 degrees, which is equal to a -1, right? Very important that we can look at that. So let's take those values right back down here. So we know we're going to have FA delta X. This is going to be cos of 0, which is going to be 1. Let me actually write it all out. Cos of 0 degrees plus force of friction delta X cos of 180 for force of friction, which will be -1. That's 559.58. That's equal to, cos of 0 is 1, so I've just got FA delta X. And then cos of 180 is -1, so I'm going to end up with negative FF delta X. Hope you guys are with me. Guys, please try not to annotate on the screen. It does get very disruptive, right? Let me just clear. I see there's a question. I'll quickly answer that question as soon as I've cleared the drawing. So Matsobane says, let me quickly do this. There we go. So I don't get that angle from the free body diagram. Matsobane, I'm not sure I fully understand what you were saying, which angle from the free body diagram, or are you talking about the cos 0 and cos 180? Just say yes or no in the chat if that's if I've got the correct understanding of what you're saying. Quickly get my screen share back up. Sorry, you guys must just tell me when the screen share is back on the screen. If it's back, please give me a thumbs up. Okay. Okay, let's open up. Okay. That's for direction. Yes, okay. So let me quickly re-explain that, right? The angles, I'll leave the free body diagram and I'll just draw it plainly here on the side. So remember, as my object was moving from point A to point B, right? What happened is your object is moving. Here's my object, my 12 kg object. There was a force applied going in the right direction, and there was a force of friction going the opposite direction. What's important is my velocity towards the right. So we need to look at, well, what is the angle, my cos theta, the angle between my motion and the angle between the force that's being applied. So in this case, my motion is going like this. My motion is going like that. So if my force applied and the motion are in the same direction, that means it's going to be an angle of 0 degrees, right? Because they're in the same direction. But if my motion is to the right and my friction is to the left, that means that angle is going to be 180 degrees. That's why I then end up with a situation where you can see there that 180 degrees for my friction. When I do my work done by friction, I end up with a case where my cos theta is cos 180 because friction is in the opposite direction. That's how I get that, which will give me a -1. And then the work done by my force applied is cos 0 because they are operating in the same direction, the same line of action that we're looking at in that case. I hope that makes sense to you guys, and then we'll continue with this particular question. Right, so I started with my equation 2 and I've been trying to work it down. So we can see now there's a slight challenge because we have now been given the fact that, so we initially had only 2 unknowns. We had F applied and the force of friction. In my second equation, I still have F applied and force of friction, but I've also now made something weird. I've given myself a third unknown, delta X, but that's okay. That we can solve, right? Because we were given another piece of information. This is the information we were given, that 42 newtons, that the force of friction acting from point B to C is 42 newtons larger than the force of friction between A and B. So what I'm going to do, I'm going to take equation 1 and equation 2 and substitute them both into this equation here, because that is really how I begin to solve everything together. And then that is going to help me bring everything together for what I'm working on in this particular equation. So I'm going to take that, and then once I've worked that, it's going to really help me solve my problem there. Okay, so let's bring that in to my particular equation here. The fact that my frictional force from B to C is equal to my frictional force from A to B. I mean, not equal, but it's 42 larger. And then when we do that, it helps me actually break down the fact that from B to C, right, this is frictional force from B to C. And actually in the second equation here, it's the frictional force from A to B. And then I'm going to substitute the fact that now I know the relationship from B to C and A to B. I know that relationship, right? And then when I substitute that equation there, then I'm going to basically work. So when I substitute that other one and it comes down, I should be able to get an equation that will be a lot more useful and a lot more fruitful for me to be able to solve. So let's put those two things together, and then it'll get us to an equation that we can actually solve, right? So in that case there, let's quickly do this. So I'm going to write that down quickly again. So my force of friction from B to C is equal to my force of friction from A to B plus 42 newtons. I think, let me just double check. That is what they said. Yeah, 42 newtons larger than A to B. So then you got A to B plus 42. And I need to put that all together. So in that case there, let me start in this case, and we can see in that case, I can change the B to C force of friction to my A to B force of friction, like that there. So from equation 1, I can then easily then say, okay, equation 1 looked as follows. It said 0 is equal to my force applied minus my force of friction from B to C, right? And I now know that this actually equals that. So I can say 0 is equal to my force applied minus my force A to B plus 42 newtons, right? That's a useful thing that I can then take and then substitute that into any one of my other equations. So if I take that, I now know that if I quickly do this for you guys, I'm going to say my force A minus my force of friction from A to B is equal to 42 newtons. If you have a look at that, I want you to see the similarities between this statement I made here and where I need to eventually put it in. So in this equation there, I'm going to have what? FA minus FF times delta X. FA minus FF is exactly 42. I can substitute that directly in and then get an answer. So let me take this equation and then take it down, and you can see it's a bit of a very hectic simultaneous, but we should be getting there. So 9,58 is equal to FA delta X, right? Minus force of friction delta X. I see there's a question there in the chat. Someone says not 42, but minus 42. Thank you for picking that up. You are correct. That if I do move it across, it's going to become negative 42. Thank you for that. Over there. So with this here, I'm going to keep this going. So 559,58 is equal to, I'm going to take out a delta X, and you'll see I'll be left with FA minus the force of friction. This is the same thing as my friction from A to B, right? Let me even write it as that. My friction from A to B times delta X. And then again, we can clearly see that what I've got is this thing here is the same thing as that thing there. And if I substitute it in, I now have a value, and I can then just solve my equation directly. I can solve it straight up, and then we'll get an answer that we can work as our final answer. So we have the fact that 559,58 is equal to, now I can substitute that value in, my negative 42 times delta X, and then we can solve for X. The only thing I want to just double check is why, sorry, because I'm going to get a delta X of a negative value, which I shouldn't be getting. It should be a positive value that I'm dealing with. Let me quickly just double check if I had done something incorrectly here. Give me 2 seconds, guys. So my frictional force from B to C is equal to my frictional force from A to B plus 42, right? Which is fine. And then if I put that together, I should get my one force minus my other force equals 0, which is correct. And we know that the force from B to C is equal to the force from A to B plus 42. Okay, I see exactly where I went wrong. When I substituted, I didn't put brackets. Maths is very important. So let me do this here. When I substitute this, I should have put brackets around here. And then when I put the brackets there, right, what you then get is 0 is equal to FA. The negative must go into both of them. So the negative goes here and the negative goes there, which will be negative, the friction from A to B minus 42 newtons, which then goes back to my previous answer of the F of A minus the friction of A to B equals 42. And then I can substitute it as 42 because I needed to be a positive value. There we go. And then my delta X is going to be 559,58 divided by 42. And then if you put that in your calculator quickly, you should see that you get an answer of 13,32 meters. I know that was a little bit of a tricky one. Thank you very much, Masero, for your answer. You did really well there, right? So it was a little bit of a tricky one. It was quite a bit of a complex problem. I'm going to quickly go back to the beginning and show you guys how we can work this question again, right? Just as a bit of a recap to help us. So let's quickly go back to the beginning and see how we can solve this. Now, what we were given was the same frictional force F now moves the block at a constant velocity, right? From B to C, I've got no acceleration. Across a rough horizontal surface from point B all the way down to point C. Force F acts parallel to the horizontal surface, as we can see from B to C. So what I was saying is that we need to find a bit of an action plan, right? So what I wanted to do in the first place was I'm going to find the FBC, use that to find the force, the frictional force AB, and then take that to my equation. I couldn't do that because I actually didn't have the value for my force that was applied. So what I really had to do now is take the same steps, but then leave them in the form with variables and solve it simultaneously. So I'll take the same steps and say, okay, that's okay. The way I was going to find my frictional force FBC was to note the fact that for the second part of my equation, my F net was equal to 0. Why is F net equal to 0? Because I was told that I've got a constant velocity motion, no acceleration. And using that, I can develop this equation here. And that equation helps me identify the fact that my F applied is going to be the same thing as my force of friction from B to C, right? After that, if I had the values, I was going to essentially solve for this value and substitute this value into this equation here. I didn't have the value, but I'll take the same step anyway. And the same step is to then say, well, I also know the fact that my work done by non-conservative forces is going to be the work done by my force applied and work done by my force of friction. Because as I do that, I need to go and find my non-conservative forces. When I look at my free body diagram, my force normal doesn't do work. Why? Because any force that is perpendicular to my motion doesn't do work. I can cancel that out of my work calculation. My force of gravity is what? It's a conservative force, like I've said. So I can cancel that out of my calculation as well. So I'm left with two forces, my force applied and my force of friction. And those are my two forces that are non-conservative. And the work done by those forces will add up to my WNC. So then I come back and say, well, my WNC is going to be equal to the work done by my force of friction and the work done by my force applied. Very important. That's my second equation. And then I'm going to work those two equations. Then I start substituting the values that I've got for that equation as far as I can go. Very important. The directions that we're dealing with, cos theta, this is cos 0 because my force applied is in the same direction as my motion, right? If you go back, you can see from A to B, this object is moving up the incline because of the force that's pushing it up the incline. The angle between them is 0 degrees. Then I need to look at the next thing. The next thing is going to be my cos 180. Where does that come from? It's because I'm moving forward, but my friction acts in the opposite direction. that is going to be 180 degrees that separates those two forces, right? One is going forward, one is going back. So that's going to be cos 180. Cos of 0 is equal to 1. Cos of 180 is equal to a negative 1. So that's going to basically make this fall away and gives me FA times delta x. And then the cos 180 basically is going to give me a negative 1. That's where this negative comes from, which changed my positive value to a negative, right? And then again, that force of friction is the force of friction from A to B in this case here. Now that I've got that equation there, I need to now somehow link those two equations together, because now I've created a little bit of a situation for myself. I had the force applied, I've got the force of friction from B to C, I've got the force of friction from A to B, and I've got delta X. There's a lot of things happening. But if I go back and remember, I was given the fact that my force of friction from B to C is 42 newtons larger than my force of friction from A to B. If I take that and I put that into an equation, right, I'll say, well, in this case here, going back from my equation 1, where I said F net's equal to 0, which means my force applied minus my force of friction will give me 0. That's why I have a constant velocity. I take that equation and then I do the thing that I've just learned, that FBC is 42 newtons bigger than F of AB. If I plug that in there, it gives me this equation that I've got down here. And then when I put that together, I can see, oh, I've got FAB minus, F of A, the applied force, minus FAB. And in the equation I had above, I've got this FA minus this FAB. I've got a number to replace both of these unknowns. And then if I do that, I take those unknowns, I put them together, there's a number that replaces them. And if I do that, that number is 42, right? Then I've simply got a single unknown to work out, which is my distance. And then in that case, they substitute the values, and then you get your delta X is equal to 13.32. Okay, I hope that makes sense. Let me just see in the chat. Someone just complaining about network. Not a problem. We will put that up on our YouTube. We're getting that done slowly but surely. All right. Hope that question helped everyone. It is 23 minutes past 7. I'm going to maybe pause for a second to see if you guys have any questions. If you guys are happy and you don't have questions, I'm going to do another question like this. If you want to first ask questions, I'll give you that opportunity. So you can either post your question in the chat, or you can maybe put a hand up and then we will give you an opportunity to speak. I'll give you guys 2 minutes to get your head around that question. Then we'll maybe do another question if we still have time. Okay, I don't see any questions in the chat. So if you guys are happy, I'm gonna then move on and we'll do another question. Duncan's asking, why did we get data today? Because you have to attend the lessons and you need data to attend the lessons, Duncan. Guys, please remember the whole issue with data. Make sure you give us constant numbers, guys. Number one, attend the session fully. Then you'll get the data. Number two, what you need to do is make sure after attending the session fully, right? Give us the correct details, because sometimes you guys change phone numbers and then we will top up the number that we know that you've got. And then that becomes an issue. So please make sure you give us the right details. Number one. Number two, attend the session fully, and that's where you get data for the particular program. All right, cool. No more questions. Let me jump straight into the next question that we're going to do for today's lesson, right? So the next question we're going to do today will look as follows. Let me quickly go to it. Okay, there's our next question. Question 5. Question 5 then says, an electric motor pulls a 20-kilogram crate from rest at point A up at an inclined, at point A up an inclined plane by means of a light, inextensible rope. Right? The inclined plane makes an angle of 18 degrees with the horizontal. B, C, and D are points on the inclined plane, and the distance between points A and C is 15.6 meters as shown in the diagram below. Let's quickly go back and see if there's any important information we need to pull from this question, right? So an electric motor pulls a 20-kilogram crate, so the mass is important. From rest, remember we had that. So from rest, what does that tell us? Rest tells us that our initial velocity here was 0. At point A, up an inclined plane by means of a light, inextensible rope. The inclined plane makes an angle of 18 degrees with the horizontal. That might be useful. B, C, and D are points on the inclined plane, and the distance between A and C is 15.6 meters. That's useful there, as shown in the diagram below. Cool. Let's jump in and start answering our questions, right? So question number one. So that's also important. Okay, 5.1, define a non-conservative force. We did this and we're going to do it again, right? Non-conservative force is a force whose work, right, done is independent of the path taken. Very important. It's a force whose work done is independent of the path taken. Let's quickly write that together. I'm actually going to just copy it from what I wrote in the previous question. Let me quickly go copy it because it's the exact same definition. Oh, that's not what was supposed to happen. Okay, let me just write it out. Sorry about that. Okay, so again, it's a force whose work done is independent of the path taken, right? 5.2, there's that very important thing I told you about, using energy principles, right? Using energy principles, you need to calculate the speed of the crate when it reaches point C. So using energy principles, so this object starts from rest, as we were told, right? It's got a force that's acting on it. From this electric motor, we're given the value of the force. It's going to cover a distance of 15.6 meters, and there's a constant frictional force that acts on the object. Using energy principles, we need to go and find, right, the speed it's going to reach at that point. So remember what steps we said we're going to do. Number one, you must ask yourself the following question. We go back to our flow diagram. What forces are acting? Is it gravity only? If it's gravity only, conservation of mechanical energy. It's not just gravity, right? We also dealing with non-conservative forces. So if I've got a change in velocity, I need to then account for that with W net is equal to change in EK, or if I'm changing velocity and elevation, I need to account for those changes in elevation. I'll use W and C. So in this case here, I'm going to go back and say, okay, looking at this question here, I've got a change in velocity from A to C. There is a change in height, but I don't know what the change in height is. So I'm going to avoid using W and C because then I have to find the change in height. And I don't want to give myself extra work. I'm going to stick with work energy theorem. W net is equal to change in EK. because at that point there, I've got the initial velocity, I must find the final velocity, and then I can work out the work done. So before I go far, one thing that becomes very important is to figure out what forces are acting on this object, right? So I'm going to just draw myself a free body diagram just so that I don't make mistakes. So let's start with a reasonably sized dot. And then the first thing I know, it's going to have an FG, right? Over and above my FG, this is acting on an inclined plane. Let me quickly do that there. So from my inclined plane, I've got a force pulling me upwards, which is the force of that electric motor, right? Let me just make my line straight. There we go. So I've got my force applied or force electric for my electric motor, right? And then I'm going to have, I was told that there's a frictional force acting there. So I'm going to have frictional force acting vertically down like this. The object is resting on a surface, so it needs to have a normal force that's going to be perpendicular to my surface in that way there. Then make sure that I've covered all my forces so that when I go and do my work done calculation, I know what I need to then work on. So looking at my forces, which forces do work, which forces do not do work. So I've got normal force, perpendicular, right? Normal force does not do work. We know that. I've got the force of my electric motor. Electric motor is going to do work because it's going to be applying a force in the direction of motion. Frictional force will do work. It'll do negative work. It slows me down in the process. And gravity will do work because I am moving up and down, because where I end up at C is going to be a certain delta H from where I started, right? So then my gravitational is also going to do work because I am moving up and down. So those three forces are going to be forces I have to consider when I do my W net equation. So let's jump into our equation and see how we can put it all together. So I know work energy theorem, W net is equal to my change in EK, right? What is W net? Is the sum of all my forces, right? So we're going to have work done by my electric motor. We're going to have the work done by gravity. We're going to have my work done by friction. All of those work put together must equate to a change in kinetic energy. That's going to be half mass times Vf squared minus Vi squared. Now let's break this down even further. Work done by my electric energy is going to be the force of that electric energy times and then you have to use the distance. Sorry, guys, I got disconnected. I'm going to just get my screen share back up. Apologies, I did say connectivity is a bit of a challenge for me today. Give me 2 seconds to get my screen share back up. Theo, you walked away with the hotspot. No, it's fine. Yeah, but no, we're back online. We're back online. Apologies, guys. You must blame Theo. He walked away with the hotspot. Okay. I'm gonna just get let me see if my chat is back up over there. Okay, please make sure, if you guys can hear me, please give me a thumbs up. Sorry, my network was unstable at that point there. If you can hear me and my screen share's back up, give me a thumbs up. Either in your yeah, there we go. There's lots of thumbs up. Let's continue with the question. Thanks, guys. Apologies for that. Yeah, connectivity is not our friend today, but we're going to finish the session. Don't worry. So let me quickly just repeat what I was doing. I don't know where I got disconnected, right? So again, we were going back and looking at which forces do work. So we said normal force is perpendicular, does not do work. The force by that electric motor does do work. Fg does do work. Force of friction does do work. And now when we were looking at it together, we said the force by the electric motor, we're going to say force times delta x times cos theta. For Fg, we can either do two ways. We can use Fg directly and work out the vertical height, but I don't want to give myself that work because we weren't given that value. So I'm going to use the slant height and Fg parallel. That's going to help me a well because that's easier to calculate, right? So then I'll do that, and that's where I got this statement from. To finish off my equation, I'm going to now say also the work done by friction. So work done by friction is going to be my force of friction times delta x times cos of theta. Let me just move my free body diagram out of the way. Right. And that must equal half mass Vf squared minus Vi squared. Nice long equation. We can start substituting our values and then solving for this particular one, right? Now, in substituting, the force of the electrical motor, we were given as 96.8. So I'm going to then put in there 96.8 newtons times my delta x, we were told, is 15.6 meters. That's 15.6 times cos theta. Remember, my electric engine is moving in the same direction as the engine's force is going up the incline. My motion is up the incline. That's going to give me 0 degrees. So I can quickly put that into my calculator here. That's going to be times cos of 0. Great. Fg parallel is going to be the same thing as mg sine theta, right? Fg parallel is going to be mg sine theta, which we can then plug in as follows. My mass was given to me as, let me quickly double check, 20 kilograms. So that's going to be 20 kilograms. Gravity is 9.8 times sine theta, and the angle there is going to be 18 degrees, right? Times cos theta. So we have to put in that times cos, and then Fg parallel, remember, Fg parallel acts in what direction? Down the slope, right? Apologies, guys. Yeah, this network is really not on my side today. I got disconnected again. I'm going to try and just rejoin the session. Give me 2 seconds. Okay. Sorry, guys, I am back. I'm back now. If you can hear me and you can see my screen share, please give me a thumbs up in the reactions or give me a thumbs up in the chat. There's some thumbs up there. Thank you so much. Again, very, very sorry for the connectivity, guys. I really do apologize. Next week, we're back in the office, so we should have much better connection for our sessions. All right, let's quickly pick up where we left off. So we're busy doing this one here, which is substituting for the work done by gravity, right? Where we said the first thing, Fg sine theta is going to be Fg parallel. So we have mg sine theta, right? Because that's how Fg parallel is. And then finally substituting our angle, we said the fact that FG parallel, right, acts down the slope. That's FG parallel, while my motion, my velocity is up the slope. And if my force is acting opposite my motion, I'm dealing with cos of 180 degrees. That's very important. So when dealing with cos of 180 degrees, I need to plug that in to my calculation. That's going to be cos of 180 degrees. Now I've covered my work done by gravity. Then I need to do my work done by friction, which is going to be the force of friction. That value was given to me is 13.5, right? That's 13.5. My delta x, we know, is the same delta x we've been dealing with the whole time. Yo, I forgot delta x for the previous one. She's nearly made a very big mistake there. The delta x here is going to be 15.6. 15.6. Then let's do our delta x, which is 15.6. And then for our work done by friction, same situation. Friction is acting in the opposite direction as my motion. So motion is up this way. Motion is there. My friction is going to be downwards. Therefore, we're dealing with 180 degrees going backwards. So cos 180 is going to be there. The value we substitute. Let's quickly do that. Times cos of 180. And that must all be equal to my change in EK, half mv squared. I'm going to write it down in the next line because it's a very long calculation. So that's half. My mass was given to me as 20. My final velocity, let me give myself a bit of space here. My final velocity, we have as initial was 0. My final velocity was given to us. Oh, no, sorry, we're calculating it. VF squared, my initial velocity was 0, right? 0 squared in that case. So there's my long calculation. I need to do all of that just to find this value over here. So I'm going to give you guys a chance to plug that into your calculators, right? For the sake of time, what I'm going to do is let me quickly, I already pre-calculated this particular answer. So let me give you the answer and then you can, in your own time, go back and try and do the question, right? So if you take all of that and you plug it into your calculator, you'll find a final answer of VF is equal to 5.96 meters per second squared. And they said, calculate the speed. So I don't need to find the direction because speed is a scalar, right? So then that's what I've got there as my speed at point C. That's that velocity here, which is going to be 5.96 meters per second. All right. 5.3, calculate the minimum average power, right, dissipated by the electric motor to pull the crate from point A to C. What is the minimum power? The minimum average power, very, very important, is they're giving us, this is minimum average power, right? Dissipated by the electric motor to pull the crate from point A to point C. And if we're dealing with average power, right, we can very easily go and from our formula sheet, there's an equation that says P average is equal to my force times my velocity average. So how do I find average velocity? Let's remind ourselves. So V average is equal to V1 plus V2 over 2. That's how you find your average velocity. So let's plug those values in. We know the force that this electric motor is pulling with, that's 96.8 newtons, right? So the force is going to be 96.8 newtons. My average velocity is V1. So let's say the velocity I started off with, that's going to be 0 plus V2. I just calculated V2. It's going to be 5.96 and then divide that by 2. Take that and plug that into your calculator. And then what answer would you get? You guys should have an answer that looks like this: 288.46 watts, right? Watts is going to be a capital W. That is the unit of measurement for power. So the average power dissipated by this motor is 288.46 watts. Next question, when the crate reaches point C, the rope breaks, right? Crate reaches point C, the rope breaks. The crate continues moving up the inclined plane, comes to a stop at point D, then slides down the plane past point B. So remember, this crate is doing this. So we've got a crate here that it starts at A, it gets pulled up until it gets to point C. At point C, this cable snaps, right? And then when the cable snaps, it goes up because it had initial momentum, right? It'll continue up to D, then it'll go back down past point B. Hope that makes sense what the question is saying. So I'm pulling crate from point A, it gets pulled up, 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 up. At point C, the cable snaps. But because of the momentum it had, it will continue going up to D, get to zero velocity, and then slide all the way back down again past point B. So very, very important. Is there a question in the chat? Thanks, Theo. You divided velocity. Wait, you divide velocity by 2 as always. Edio, I'm not sure I fully understand your question, but let me quickly go back to that calculation. So when we are doing average velocity, right? Remember, average is going to be your average between, it's your mean between two things. If I got 60% for paper 1 and I get 80% for paper 2, and someone asks me, what is my average mark for physics, right? Then I'm going to say, I'm going to take mark number 1 plus mark number 2 divided by the number of tests I wrote, right? So it'll be 60% plus 80% divided by 2. If I had 3 exams, I'm going to then say, well, mark number 1 plus mark number 2 plus mark number 3 divided by 3. In this case, my average velocity, I've got the velocity I started with, the velocity I ended with, and then I'm going to add those 2 and divide by 2. That's why I do that over there for my average velocity. But you should find this on your formula sheet as well, the equation for that. Just a quick reminder, guys, please do not annotate the screen. It is very disruptive for myself as the presenter, and I lose where I am. And it's also very disruptive to the fellow learners who are watching the session. And you guys, I'd like to believe you guys are adults, and we all need to respect each other. And that's how we engage with these sessions so that everyone gets the best of them. Great, guys. Okay, let's quickly go back after now understanding what this next question is asking us, that the crate reaches point C, the rope breaks because it was moving at a particular velocity. The momentum keeps it going up to point D, reaches now maximum height, 0 velocity, and then it slides back down past point D. Draw a labeled free body diagram for the crate as it slides down the plane past point B. Okay, let's look at what's happening. At point B, this crate is sliding down, right? What is making it go down? Gravity. There's no force making it go down. It's just gravity. The other forces that are at play, there's friction because my inclined plane is said to be a rough inclined plane. And then there's going to be force of gravity because this object is going to have mass. Finally, we will have a normal force because it's resting on a surface. So then I'm going to go there. First of all, do my reasonably sized dot. Have a force straight down. That's going to be my force of gravity, right? I've got a frictional force. Now with the frictional force, I'm going down the incline. Friction is always opposite to my motion. So my frictional force is going to go up the incline. So there's my force of friction. And then perpendicular to my surface, I'm going to be dealing with the force normal. There's no force going downwards, guys. Very, very important. No force going downwards because the force, the thing that's making me go downhill is gravity, not any other particular force, right? And then if you do want, you can do the other way. Like I said, it's my personal preference not to do it. Not that it is an incorrect method, but I will show you the other way of doing this. So again, up the incline, we said we've got our force of friction. Down the incline, if you want, what you can put is you can put your FG parallel perpendicular to my surface. I've got my force normal. And then opposing that, I'm going to have the Newton's third law sort of reaction force to my normal force is going to be my force of gravity perpendicular. That is also another way of doing it. It does also help sometimes with calculations to make sure you've got the right value for what you need to do. Then 5.5, it says draw a velocity time graph for the entire motion of the crate, starting from point A until it passes point B, again on its motion down the inclined plane. You see, guys, it's very important when dealing with physics not to treat things as silos. Look at how they're bringing a concept from another topic into this topic over here. That's why it's good to know physics as a discipline entirely, right? Very, very important. But that's fine. We did this thing about 2 lessons ago. We were doing vertical motion, and I showed you guys the key tips and tricks for doing vertical motion, motion graphs. So let's first think about how the motion is going to look. Let's quickly go back and recap what happens. So in our recap, we have the following that's going to happen here. We have this object. Remember, it's initially moving at a constant velocity, right? It pulls a crate. Oh, no, not constant velocity. Sorry, it was accelerating constantly up the incline because it started at 0 and it got up to this velocity, 5.96. So it was accelerating. My acceleration was not equal to 0. So I've got acceleration going up, constant acceleration from A to C. From A to C, it snaps, right? Then it's going to move up to D, up to 0. So it's going to be negative acceleration from C to D. And then it's going to now speed back in the opposite direction, going all the way straight back down. Okay, let's have a look at how we can draw that graph. Let me quickly just create space for myself here. Okay, so let's look at how this graph will look. Let me draw my axes. They said I must draw a velocity versus time graph. Showing the motion. Come on. At all the various points there, right? And then starting from point A until it passes point B again. So remember, let's map what happens. So initially, the first motion, what is happening? The first motion, we've got that object accelerating from A to C, right? Constant acceleration from A to C. In this graph, we've got velocity versus time. So if you think back, constant acceleration means my graph is going to be a straight line going up like that, right? I'm going to have a straight line going up like this from point A to point B, starting off at 0 velocity. So then I'm going to just take that moment there and say, okay, I'm going to start off at 0 and I'm going to accelerate constantly from point A to point B. Very important. So there's point A and this here is point B. So it's now I'm dealing with positive acceleration. I'm assuming that up and to the right is positive. At some point, the cable snaps. When the cable snaps, now I'm under the effects of gravity, right? So my acceleration used to be up. Now my acceleration is going to be in the opposite direction, right? I'm going to speed down that way. But before I speed down, I had a velocity that's not 0. Remember, where am I? My velocity is here. That's not a 0 velocity. I need to speed back to 0 first or slow down to 0. So from point B, sorry, not B. This was point, what is this? This was point C, not point B. So this was point C up here. Then from point C, I keep going up until point D. So from C to D, I'm continuing in the upward direction, but I'm slowing down. My velocity is going to slow down until I hit 0. So then let's quickly go back and show that part there. My second part of my motion is now I'm accelerating, but now I'm accelerating down the slope, right? From C until I get to D, which means my velocity has got to be 0. That's my maximum height. So from C until D, I'm going to slow down. So from C, I'm going to start there, and then I'm going to slow down until I hit D. Let me make that a little bit bigger so you guys can see it more clearly. So from C until D, my acceleration is going to be negative like that there. Okay, down to 0. So this is now point D that I've reached. And then from D, I'm going to start now moving in the negative direction. So I need to be below my x-axis, that's negative velocity. And I'm going to be now accelerating down past point B, right? So as I do that, I need to think about how that's going to happen. I might not have the exact values, but then at some point there, the last motion I'm going to have, let's put that in orange. So my motion 3, or the third part of my motion, I'm going from point D to point B. And again, I am still accelerating down the slope, right? So I'm going to have negative acceleration. Remember, up the slope, I'm defining as positive. Down the slope, I'm defining as negative. So if you look at my gradient from A to C, it's positive motion, and positive gradient means positive acceleration. From C to D, my motion is positive because it's above the x-axis, but my acceleration is negative, hence my gradient is negative. So from D to B, again, I'm moving in the negative direction, so I'm going to be under my x-axis, and I'm accelerating negatively, which means I have to have a negative slope still. So I'm going to have a negative slope as well. And in that case there, I'm going to have a line that just looks like this. Let me just make that thicker so it can be clearer for you guys to see. I'm going to have my acceleration, again, look like this. And at that point that I've reached, that's going to be my point B. If that graph makes sense, please give me a thumbs up if you guys are happy. If it doesn't make sense, tell me exactly where you need me to clarify. Remember, we're going to try by all means in this group not to say, sir, repeat. Tell me where exactly you are finding the challenge, and I will help you clarify that one point. Okay, there's thumbs up in the group, 2 thumbs up, 3 thumbs up. Thank you. If it doesn't make sense, please ask me specifically, where do you want me to explain? What do you specifically not understand? So Poloso says from A to C, I don't understand, right? Okay, so Poloso, let's quickly have a look again at what happens. So A to C is going to be very simple motion. So remember, this block is sitting here at rest, right? Remember, what does rest mean? It means I've got a velocity of 0, sitting, purely doing nothing. This electric motor starts pulling me up. So my velocity starts at 0. Then it's going to increase because somehow at point C, I'm already moving at, what was the velocity given? I can't remember the speed exactly, but I think we calculated that speed. We're moving at a speed of, there we go, 5.96 meters per second. So if I go from 0 to 5.9, it means I have increased my speed over time. Increasing speed over time means I'm doing what? I'm accelerating, right? So when you go back to your function, you can see on your graph, you need to start from 0. And at some point up here, you're going to have a velocity of, let me quickly bring my ruler in. At point C, I need to have a velocity there of 5.96 was 5.96. So my velocity there is going to be 5.96. This is velocity in meters per second. This is time in seconds, right? So that's the speed that you're going to have at that point there. I hope that makes sense from point A to C, that I started off with a velocity of 0. And then by point C, I was moving at a velocity of 5.96. Then from C to D, what happens? So remember, you're moving up at a particular velocity from here up to point C. At point C, the cable that's pulling me up snaps, right? So I'm going to stop because that's what was pulling me up the incline. But I won't just stop immediately, right? I have to slow down over time because I've got some momentum that I need to sort of brush off, that I need to finish. So from C to D, I'm going to move, but I'm slowing down until I reach maximum height there at D. And at maximum height, what is the velocity? Velocity at maximum height is always 0. So if I come back down now, I can see. So from C, my cable snaps. I stop accelerating upwards and I start accelerating in the negative direction. So my velocity goes from 5.9, 4, 3, 2, 1, 0. At point D, it's maximum height. My velocity stops, right? I'm at 0. I stop moving completely. Then gravity is going to act again. It's going to keep going. What's going to happen from D is I'm going to slide back down the incline. And then I'm going to slide down the incline at an increasing rate until I get to point B. If that makes sense to everyone, give me a thumbs up in the chat or thumbs up in your reactions. And that brings us to the end of our session for today. I'll give you guys a chance to ask any questions still in the next 5 minutes. But I hope that was really helpful to you guys. Okay, I'll give you guys some time to think up of any questions you've got, but I am here. In the meantime, thank you guys. It's been a great week. Massive apologies for our difficult technical challenges this week, but we're back in the office next week. So we will end up with better connection. We're going to put the rest of the recordings up bit by bit. Apologies, guys. It is taking time because we do have to sort of cut some parts of the video out. So it requires a little bit of editing on our side. So, but we are going to put them up. The functions video is already up. The trigonometry video from yesterday it should almost be up on YouTube. I think it might be up on YouTube. If it's not, it should be up at the end of this lesson. And then I'm going to start uploading the science videos as well. So slowly but surely, we're getting the sessions up on YouTube in that way. So I've got no one asking any questions. And if that's the case, then we're going to end off today's session, guys. Thank you so much. It's been really awesome engaging with you guys. I hope you guys have a great rest of your day. Someone's been there. Matsubani, I've been attending and I haven't got any data and I'm registered. Matsubani, please just send me a direct message with your phone number. And I'm assuming Matsubani Mangwan is your full name. Send me your phone number directly. Don't post it in the chat to everyone. I'll double check with our team and then just make sure as well. I'll just write your name down on the board as well, just to put there.
Sorry, Ernest. I think from the previous session, we did check Matsobani on our registration list and the invites that were sent to the schools, and that name did not come up.
Oh, okay.
So if the Matsobani can maybe go speak to the tutor, but with the letter that was sent, their name was not there. So the tutor can let us know.
Okay, no, that's fine. Yeah. So guys, and I think another way that's going to be very useful, please just let your tutor know at your school, right? The challenges you're facing, and then the tutor, what they'll do is they'll engage with us and we'll take those on a case-by-case basis. Remember, there were specific names that were submitted from people's schools. If your name was not submitted, it is okay that you join the sessions. It's just that then the data will be allocated for specific learners because there is a budget that we have to adhere to on our side. But thank you guys very much, and thank you, Nell, for that feedback. That is quite helpful. Okay. Awesome, guys. Thank you so much. It's been a great session. I hope you guys have a great rest of your evening. Have a great weekend. Get some rest, but also do a little bit of studying. Let's not let our brains go to complete waste. And then we will all see each other next week, Monday, for our next maths lesson. The next lesson for next week, let me quickly try and see what our topics for next week are going to be. The topics for next week are going to be, I'll tell you now. So next week's lessons are going to be Monday, we've got Euclidean geometry. Tuesday, we've got the Doppler effect and rates of reaction. Wednesday, we've got analytical geometry. And then Thursday, we're going to have one of my favorite sections in chemistry, chemical equilibrium. So we're going to have some fun next week. We're getting into some chemistry. We've been doing a lot of physics, and then we're going to do a little bit of chemistry as well. We did some organic chem this week, but next week we're going to my favorite chemistry topic, chemical equilibrium. Guys, it's been so great. It's been so awesome. Please don't forget, if you want to get more of our content, while this weekend, just in case you miss us, just go to our YouTube, go to our TikTok. That's where you can access a lot of our content. Until we meet again, we'll see you guys next week. Cheers, guys. Have a great one. Goodbye.